this on.
So the next talk is evaluating soundness of a gradual verifier with property-based testing by Jean-Paul.
There we go. Okay, is that okay? Yeah? All right, perfect. All right, so I'm gonna start. Yeah, so this is evaluating soundness of a gradual verifier with property-based testing. My name is Jean-Paul from Cornell University, and this is work with Jenna White, Jonathan Aldrich, and Joshua Sunshine from Carnegie Mellon University. Oh, about that. All right, so let's begin. All right, so what is gradual verification? Why do we care about gradual verification? So first, we'll start with dynamic verification. So here we have an example where we have a function that wants to return the maximal element of a list, just find max, pretty simple function. So for dynamic verification run, all we do is we run a post condition to ensure that we get the recursive function's max result L and contains result L. So as a result, these functions are ran after each execution of find max. So as you can probably see, this is going to be very computation heavy. So this is going to be very computation heavy because it's going to run every single time. So we have a lot of runtime overhead, and also, unlike static verification, dynamic verification doesn't provide the reassurance that the functions are going to be true for every possible execution of find max, because it's going to run at runtime. So now let's look at static verification instead. So static verification has the benefits of static guarantees, in which we have zero runtime overhead as well, and we do actually formally guarantee every execution path for the program. So first, we have to include a precondition to make sure a function doesn't run an empty list. I'll put this here so you can see. So first, we put a precondition to make sure, so L is a null. Then we need a series of loop invariants to reason about the while loop. So you can start seeing how this gets very, very long. Then we need a series of folds and unfolds because the recursive functions won't be dealt with automatically. So you have to manually actually define the folds and unfolds for unrolling the recursion that happens with those functions. And then finally, we need helper lemmas because the toolkit can't discharge proof obligations for these recursive functions either. And as you can see, it results in a very, very long specification that just goes outside of the box even. So it doesn't support incrementality, essentially. And another thing as well, we're forced to check the correctness for every specification rather than a specific thing. So if we just wanted loop invariants, we can't just write the loop invariants. We're forced to write every single thing. It's all dependent. So here, we introduce gradual verification instead, where it mixes both of them. So with gradual verification, it allows developers to deal with the costs from static verification, but at the same time, you can also choose to just leave stuff blank, leave it as an imprecise state, as you can see with the question mark there. So the gradual verification will provide feedback on any specification increment, statically where possible, and dynamic when necessary. So ideally, if you statically specify everything at 100%, you just have a normal static verifier. But if you start leaving imprecise states with those question marks, then you'd have less security, obviously, but it's still pretty good. I'll explain now in a moment as well. So so we can see there that we start by just removing the precondition, making it imprecise. So we decided not to write anything there. And then also we're removing the loop invariant specifically as well. Yes, so then, okay. So now we go a step further. As I said, you can keep specifying as much as you want. So now we're going to add more specifications to get more static feedback from the gradual verifier. So this time we're going to use separation logic. So we're going to use the separating conjunction to combine the imprecise state with the question mark that's seen first, and then the checking that it is a null. So now you've actually had to sit down and think, hey, I want to make sure that it doesn't deal with a null list, so it has more static information. So it's going to increase in rigorousness. And otherwise, we just apply dynamic verification to the rest. And then further, you can also just put the loop invariants themselves as well to have a fully statically verified program. Okay, so we can stop at any point that we want. We don't actually have to specify everything, as we've said. And so, for example, we have tests that prove that if you put in place some data invariants and you only want to specify 13 lines of spec code, this will return a 40% verification conditions that are statically verified. And the more you increment with 22 lines of specified code, then you have 86% of static reassurance. Okay, and then so these are the main important parts of the gradual verifier. So the gradual guarantee says that it is monotone with respect to precision. If it's fully statically verifiable, like at 100%, then no matter how much you remove from that static information, it's still going to be sound. Then we have the conservative extension. It follows as well. Anything provable in this statically should also be provable gradually. And then finally, we have the actual tool itself. So the tool itself is called Gradual C0. It is an extension of C0, which CME uses to teach dynamic verification, and it's extended gradually. So this design has been proven sound. And how the actual system works is that it's a static verifier with the implicit dynamic frames, something that a language like Daphne could use for static reasoning, and abstract predicates. So the way we continue on to actually do the gradualization, we do this sort of lifting, which is also called a semantic extension, in which we redefine functions, predicates, and judgments to handle the imprecise formulas. And now we have a system that can optimistically assume non-contradictory strengthening of formulas in support of proofs. And also that combined with a dynamic verification system to actually do the runtime checks, we have a full gradual verifier. So now our goal is to ensure that gradual C0's implementation is sound and allow for scalable bug fixes. So something is that there is no lightweight method or necessarily a formal proof to actually make sure that the gradual verifier implementation is sound in and of itself. So I suggest using property-based testing, or use property-based testing. So why use property-based testing? Well, a number of bugs had been caught by hand because there's no automated tool to actually catch these bugs. So this is an automated method to do so. Then we have that there are no lightweight techniques available. And finally, capturing the truthiness of a property's result has been shown to provide good coverage for finding these implementation bugs. All right. So then the property-based testing tool uses a three-stage pipeline. It starts with the reference model language, which uses Gradual C0 specification language. Just comparing the specification language, it's pretty neat that it's already all embedded. Then we have this is the work in progress part, which I'll talk later on in future work. The input generator, which is a test suite of examples that are not supposed to verify correctly. I'll explain that now as well. And then so the checker, which is two parts. It's dynamic C0 and gradual C0. Gradual C0, just a normally gradually verified program, and dynamic C0 asserts runtime checks everywhere, and it is said to be the ground truth. We already have a benchmark that's going to check the fully statically verified programs to actually compare how well our tool is doing, how we got the previous statistics from I mentioned earlier, but there's nothing to actually check if the dynamic verifier is actually breaking or not, to make sure you're doing the right runtime checks. And this is similar to something like QuickCheck that will attempt to generate test cases, and it'll reduce a given program to whatever method failed if there was an implementation bug, and then allow us to fix that implementation bug. So then here we have the checker architecture. So the checker architecture establishes dynamic C0 as the ground truth, expecting either an error or a pass from gradual C0 if dynamic C0's output is a pass. But they should never differ if dynamic C0's output is an error. The input generator is made up of a dozen programs that come from gradual C0's benchmark tests. So as I said earlier, we have the benchmarking. These are, I said a dozen programs. It's actually a dozen methods. So it's 4 specific benchmarks: list insertion, AVL, BSC. Those are the main three. There's another one. And so we have, those are 10,000 plus lines, completely statically verified. And so what we do is that we just break them, essentially. So at the beginning, this is manual breaking, making those programs do implementation errors where the specification didn't go with the implementation or the implementation didn't go with the specification. And then what we do is that we just input the program. There's an intermediate representation for gradual program. And then we first do the top part where we gradually verify it. And once that's done, we do the bottom part where we dynamically verify it. And then all we do, we have a backend that already establishes what errors there were. And so if the gradually verified program is different from the dynamically verified program, but the gradually verified program said that it was sound, then that's a big error because it means our tool is unsound then. So it should then result in an error, and we should then see where it was in the given code, that error, so then we have an idea of what we have to fix in the actual implementation of the tool. So then by example, we have here, so this is an example from the binary search tree. Very easy, just a simple implementation issue, just reverse left is going to be greater than the right node, and that's obviously wrong, it doesn't follow the specification. But it's important that these set of examples can fail trivially. So there's several things that we have to remove, like preconditions, folds and unfolds, because if the program sees that these are specified, then it's obviously going to fail the gradualizing, but it's going to fail statically instead of dynamically. So we have to remove all this static information. And so the truthiness said is that they both have to be the same, the dynamic output and the gradual output. And then here, so the input generator architecture, so we caught 4 soundness bugs at different implementation phases of gradual C0. So for this specific example, so we begin with an append method that has no permissions and an imprecise state. You can see that with the question mark in the precondition. And so when we encounter the while loop, we correctly emit a check for asserting that we have access to endpoints in X. The first iteration of the loop is fine because we have checked that we have access to endpoints in X, but it doesn't check it for the other iterations, so it should fail. But at the time, the gradual C0 actually said this code was sound, even though it wasn't checking correctly. So this was a soundness issue, which when compared with dynamic C0, you would see the difference in output. All right, and then so future work. So we want to make sure that we can catch all bugs in the verifier. So our tool will reduce to these bugs. So there's not a way currently to actually fully make this like a fuzzer for automatically generating these files. So we're not generating the inputs for the files, we're generating the actual files themselves. So I haven't figured out a way to generate gradual C0 files that are supposed to fail, supposed to have specifications that don't abide the implementations. But that's future progress. Right now, we just have the 4 benchmarks with more than 50 methods each, and those we permute through them to try and see if there's any bugs. And that would be it. Thank you.
We have time for a short question. In the meantime, next speaker, would you please set up the device. Any questions?
So the approach that you took manually, where you changed like the left and right of a comparison, for example, really reminds me of mutation testing, in which known input, you seem to know that it's. But it seems like you're doing it manually. Did you consider taking a just direct automatic mutation testing approach rather than building your own generator?
I didn't at the time of making it. Somebody did suggest that later on, and I would suppose that would work the same, but it would. I think the results would pretty much be the same in terms of the test suite. It would still be the same like main 4 benchmarks that I would have to look for, and I want to actually try and generate an example like the last one that I showed. That was just an implementation bug that was found completely separate. So yeah.
Thank you.